All right, ladies and gentlemen.
Today's class recording has started.
Today's class recording has indeed started. So let's go here. You don't have a sheet of paper in your entire bag. So. What? It makes it more authentic. It seems like students did it then, you know. So. All right. So the first part of this unit deals with introducing some different types of energy. And so we talked about kinetic energy, we talked about potential energy, we talked about the factors that affect those different types of energy, and you know, the different types of relationship, the direct relationship, the quadratic relationship, all that fun stuff. So today we're going to introduce, actually not introduce, we've introduced this concept before, but we're going to talk about the concept of conservation. And we've talked about conservation before, and I think that you've been introduced to it before, but just real quick, right? When we say that something is conserved, what does that mean?
It's transferred. It stays the same over time.
It stays the same over time. Good, that's a good description, right? That any quantity that we say that is conserved remains constant, meaning that if we measure it at some point and then measure that value later on, it will be the same. Now, a couple of things about conservation, and these things don't show up in the notes, so you might have to, if you want to jot a little thing in the margin of the paper or whatever and stuff like that, okay? So first, and we introduced this when we, before we get into that, conservation. This idea of conservation is something that is going to run through basically every unit that we talk about from now on. There are lots of quantities that we know of that are conserved in the universe, or at least we believe they're conserved. We haven't seen a situation yet where they haven't been, right? Of course, leaving the possibility that it could be in the future, but we don't think that's going to happen, but it might, right? So when we talk about conservation, we talked about momentum in the last unit, right? We're going to introduce energy here. Later on in the year, we're going to introduce mass. We're going to introduce charge. These are all conserved quantities. If we measure that quantity at the beginning of the situation and at the end of a situation, we'll end up with the same number. Now, a couple of things, right? First, conservation only applies to what we refer to as systems, okay? We'll never see conservation in a single object. Conservation involves some kind of transfer, but if we transfer something, whether it's energy or whether it's mass or whatever it is, something's going to gain and something's going to lose. What does that mean is true about the total? If something gains and something loses, what's true about the total? Stays the same, right? If one goes up, another one goes down, the total remains constant, okay? Also, when we talk about conservation, a lot of times, and we'll get this concept a little bit later on, we refer to something as a closed system, okay? The system is the two or more objects. The closed part means that we don't interact with other things. A good example that somebody brought up in class today. So when I talked about conservation, I used a box of Legos, right? You have a box of Legos. You can put them together and you can make them into a house. And then you can take that house apart and you can put them together and you can make a car. You can take that car apart and put them together and make a boat, right? Or a spaceship, right, if you're Benny.
Oh,
You ever seen the Lego movie? Yeah. You should. It's good.
well, they used to be everyone's.
You know, so but think about your job. Your job is you just make stop motion Lego movies, like that's what you do.
I think it's also great.
She does have.
I know, but when you make the Terminator away.
She doesn't.
She does.
All right, but the whole time when you keep taking those Legos apart and putting them back together and making something different, you still have the same amount of Legos.
Unless you have.
Now, So somebody from this morning said, well, what if my dog comes and eats one? That sounds like something that's happened before. And I said, okay, that now, and this is an important idea, right? Now we don't have a closed system. The box of Legos by itself is a closed system. Nothing comes into it or out of it. But if your dog comes in and eats one of them, right, now that's not closed anymore. So when we see conservation, we have to look at what we refer to as a closed system.
Would it be a closed system then if you added another one?
Well, we get back to the original number, you know what I'm saying? But, you know, depending on whether your dog ate one again or not. So technically, no, it's not a closed system if you add one, because now the box went from, whatever, 744 Legos to 745 Legos, right? But if then you had that box and started building with it again, as long as your dog didn't come and eat one or you didn't put another one in, that would be a closed system.
How about this? If you build a sand castle,
Yes.
the sand castle falls.
Okay.
The sand's still there. Yeah,
True.
But the sand castle.
True. Conservation, okay, so Edie, this is a good point. Conservation doesn't mean we have exactly what we had before. We have the same amount of stuff we had before, right? So we can take it apart and put it back together. True. But do you have all the sand? So sand is conserved. That doesn't mean that you have a sand castle all the time. It just means you have the same amount of sand, right? You have 745 Legos. What you make them into is up to you, but you still have the same number of Legos. It's actually really not. You would think that, you know, it sounds like a lot, but it's really not. So. All right. What we find is that energy is a conserved quantity, meaning that the total amount of energy in a closed system will remain constant. So a couple of things to clarify this statement. First, we just sort of discussed a closed system. Nothing in or out, meaning there's no interaction with the surroundings. Okay? Second, when we talk about energy or conservation of energy, we have to talk about the total amount of energy. All the kinetic, all the potential, all the heat, all the chemical, all the nuclear, all that type of energy. If we look at the total remains constant. We may see changes in the amount of individual kinetic energy, or individual potential energy, or individual thermal energy, but when we add the total up, it has to remain constant. Okay? Good there so far? Okay, question. See if we can recall some things and make some connections, all right? If we have a closed system, what are the only kind of forces in a closed system?
Friction. No, gravity. No.
What are you trying to do here?
Gravity. This is the gravity and what's pushing up? Closed system.
No gravity. So.
Gravity could be included, but it doesn't. That's not the only answer. If we have a closed system, what does that mean? Nothing goes in or out. Meaning that all we have is what's there, right? But any force in there has to be accompanied by what?
Another force.
Another force, right? What do we call that, Jeff?
Equilibrium.
So if we have a closed system, two objects, one pushes on the other one, what does the other one have to do? Push back, right? All of the forces in a closed system have to be action-reaction forces. Okay? I thought that's what you were trying to get to.
Yeah.
But you get to, yeah.
Pushing up and this.
Is that an action-reaction force, Edie? No.
This.
Those two forces are acting on the same object. They can't be action-reaction forces, right?
What about this?
Now, if you do this, right, gravity pulls down on something, right, what does the other gravity have to do? Pull pencil up on something else, right?
So this then.
Okay. Oh. What happened to the what happened to the earth when I dropped your pencil?
It moved.
Okay, that's action reaction. Because pencil and earth, two objects, right?
This moved.
Yeah, sure. Yeah. Right. If we consider the table to be attached to the earth, basically.
Well.
Right? So, there's that. All right. Before we move on to the next part, oh, sorry, one last question. What is the ultimate closed system? No. What?
Oh, wow.
I think a closed system is a group of objects, right? No interaction with the surrounding, yes. What's the ultimate closed system? Go the other side.
Everything.
Go the other shape, everything. What do we call that?
World.
The universe, right?
The work.
Does anything go in or out of the universe?
No.
Not that we're aware of. Right? Okay.
Nothing that you actually can't happen in the universe.
Say again?
Nothing, nothing can go out or in. Like,
Sure.
you have, like, say in the universe, like an asteroid is nothing can out or.
Well, still in the universe.
Still in the universe, though.
What's string theory?
Yeah, the universe is a tough one, right? Yeah, so do you want me to like blow your mind a little bit with the universe talk?
Yeah.
So,
Yeah. I always like universe.
So,
Have you ever read that?
so the universe is everything we know of, right? As far as we know, nothing goes in or out of the universe. And as far as we know, nothing exists outside of the universe. There are some hypotheses about parallel universes and stuff like that, but there's really no evidence to support those things. Okay? So, the other weird thing about, so let's bring it back to this. How much energy is in the universe? A lot. But what has to be true about the amount of energy in the universe? Stays the same, doesn't change. How much energy is in the universe compared to like the Big Bang? Exactly the same. All the energy that was there at the beginning is here now. It looks different, attached to different things, but it's still there. Okay? Now, one of the things that we're noticing is that the universe is expanding, getting bigger. That's, yeah, like, so there's two things there. One, wait a minute, there's an end to it? Because it's everything. And the answer is yeah, at least as far as we can see. We like look, and there's an end. There's like the end of it. What's outside of that? Nothing.
Well, what is it?
Doesn't exist.
Maybe it's not there.
Based on our observations, right?
Is it black or white?
It's not anything.
What?
It literally doesn't exist.
Oh.
Here's the weird part. Well, if that wasn't weird enough.
Guys, he did say he was gonna blow you.
It's expanding. Nothing.
What?
Yeah, exactly. Yes. So, yeah, it kind of is, but it's happening. And so it's like, so if this room was the universe, the walls are moving outward. No. Okay, so this is actually a good discussion, right? So what's happening to, see if we can put some words together, right? What's happening to the energy density? Becoming less and less. Same amount of energy, but how much are we spreading that energy out over? More and more and more. So the energy density is becoming smaller and smaller and smaller. Most of the energy in the universe is concentrated where? Stars, right? That's where most of the energy in the universe is. How much energy is there between stars? not different amounts, but not much, right? It's really, really cold in between stars, and it's really, really hot at stars, right? Eventually, if that energy just gets spread out over a bigger and bigger and bigger universe, what's going to happen to the entire universe? No. It'll become really, really cold.
Global warming.
Okay?
It's just
So, well,
infinite
infinite ice age, right? That is one of the theories about how the universe will end. Is that it'll just keep expanding, 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 and pretty soon the energy just gets spread out so thin that nothing exists anymore. Well, sorry. There will still be space, but there wouldn't be things like stars, which could lead to things like life and stuff like that, you know? It's basically just kind of like, the energy is just sort of like,
How is it expanding into nothing?
that's a weird one, CD. So,
Is it possible to expand so far that the energy can just keep expanding?
in theory, yes. That's one theory, right? Why is it a theory?
It's not true.
Well, it's not true.
What do theories do? Explain things, right? That's a theory about a possible end of the universe. That it just keeps expanding, expanding, expanding. And then we just kind of like, dies out. There's another theory which isn't very well supported, but it's kind of a cool theory, but we don't really think it's going to happen. Right? So when I take this rock and I throw it into the air, I drop it. I take a rock and throw it in the air, it comes back, right? Because of what?
Gravity.
Okay? Gravity exists on all objects, or all objects of mass, right? So if things are expanding, right, eventually, what will they do?
Blow up.
No.
It will. Then you
What happens to this rock because of gravity?
won't be able to pick it up.
On the way up, it does what?
Stop.
Well,
Accelerate.
slows down,
Slows down.
stops, and then it,
Accelerate.
Wait, so will it just stop and then go back?
that is one theory.
Oh,
But it is-
The
Like,
universe,
it's so big that-
because, right, all the stuff in the universe is attracting all the other stuff in the universe, right? So if all the planets and stars and junk on this side are attracting all the planets and stars and junk on this side, what are they doing to each other? No. What does gravity do to things? Pulls them together. It's slowing them down and slowing them down and slowing them down until eventually they'll what? Well, first they'll stop, then they'll start coming back together.
Wait, but if it gets so small, is everything just gonna get hot and it'll just turn the other way?
So how did the universe start?
Big explosion.
What we call the Big Bang. Guess what creatively we call this? The big crunch. Right?
Wait, so why don't people do this?
Here's why. And this is a weird one too. That's we still haven't figured out yet. Not only is the universe expanding, the edge of the universe is going faster than the middle of the universe.
That was the middle of the universe.
What?
That was the middle of the universe.
Well, if you have an explosion, right, boom,
Right.
everything goes this way, right? But the edge of it is getting faster. So the leading edge of the universe is getting farther away from the middle, and so it's like getting bigger and bigger and bigger, spaced out. Kind of middle-ish, so, But that doesn't make sense because if this happens, right, it slows down, it doesn't get faster, unless something is pushing it. Good question.
How fast is
Oh, like the speed of light. Because if it's energy, that's like how fast it
Wait a second, hold on, back to, like, if the universe is going back.
Yeah.
So that means that there's gravity acting, but with the rock, gravity is on the outside of the object.
Mm.
If the universe is the object, then doesn't that mean there has to be gravity outside
gravity exists between two things in the universe, right? Remember, gravity requires two things, right? Gravity isn't something that something does to something else. It happens between stuff, right? So if you talk about some Earth-type planet on the other side of the universe, what are Earth and the Earth-type planet doing to each other? They're pulling each other, right? So if they go apart, eventually they would come back together.
Right, so all those planets inside the universe or would
They're pulling on the other side, and the other side's pulling on this side, and that's why we did this. Right? Wait.
is the rest of the
Yes.
Are you looking up
Ready?
what?
Ready? It's like this. Except with gravity.
Much slower.
No, actually much, much faster. So,
Oh, yeah.
yeah. So, yes, son.
How long would it take for gravity to
Well, it's been about 14 billion years since it was started expanding, and it's still expanding. So, like, and to answer that question, how long does it take this rock to go up and come back down? Well, in relation. How long does it take to go up compared to coming back down? Same amount of time, right? So if it took 20 billion years to expand, take 20 billion years to come back. That's a fun one to think about, but we really don't think
That
it's gonna
just
happen.
explains how big it is.
If we had some sort of rocket that could make it to the edge of the universe, what would you get to?
It's a good question. That's like, so if you like put your foot, that's Earth, yes.
You guys are
My
so
God.
weird. Alright, stop.
If you put your foot out of the universe, does it not exist anymore?
Like if there's a wall. I don't think it just stops.
how do you know it's rocket
That's a good question. So, because
If you pull it back
like
in,
here, how do I know I've gotten to the end of this room? The wall,
there's a wall.
right?
But we can't see the wall.
Yes, you can.
Can? What does it look like?
Well, it looks like, hey, I can see that far, but then there's nothing past that.
But how do you know?
Whoa. But that happens when I'm like looking for
That's all at this point, that's all we can go on, because we can't see it.
Maybe our
Well,
telescopes just aren't
Yeah.
powerful enough.
What?
Maybe the telescopes just aren't powerful.
That is a possibility, yes, right? But at this point, it doesn't look like anything. It's like, okay, this is it. This is the end of it. There's always that possibility too, that it's some, and that getting back to the idea that it expands and it's going faster, that's completely contrary to everything that we think we understand. So like, okay, what's happening here?
Or, what if, so if you put your foot outside of it and it doesn't resist anymore, then you pull it back in, is it?
I don't know. All right. So, sorry, that's mind-blowing universe stuff. So.
Can we keep going?
All right. I know. All right.
I mean,
So let's talk about conservation of mechanical energy. First, we talked about mechanical energy previously in the previous section. What does mechanical energy consist of? Kinetic energy, gravitational potential, and elastic potential. Okay? So, by that logic, putting it together, if we have conservation of mechanical energy, we have the amount of mechanical energy remaining the same. But what we find out is that only happens under certain circumstances. When there are only conservative forces acting on an object, mechanical energy is conserved. So that then leads to the question of, what are conservative forces, right? So what we find is that there are two types of conservative forces. Conservative forces don't change the amount of mechanical energy in a system. Gravity forces and elastic forces. And that's number 1 and number 2, or little a and little b. Little a is gravity, little b is elastic. So if they don't change the amount of mechanical energy in a system, what do they do? Well, they transfer energy from one form into another form. Okay? Conservative forces convert one form of mechanical energy into another form of mechanical energy, but the total amount remains the same. Conservative forces, when gravity and or elastic forces are acting on an object, the different amounts of mechanical energy individually will change, but the total amount remains the same. And when that's the case, we call that conservation of mechanical energy. When there are only conservative forces acting on an object, mechanical energy is conserved. Okay? Mathematically, we can represent that like this. MEI equals MEF. And if we wanted to be fancy about it, and you guys are fancy, you can add this if you want to, right? We could put the sigmas in front, right? Because sigma means what? Well, it means net force when it's in front of force, but the sigma itself means what? The sum, the total, right? So the total amount of mechanical energy initially has to equal the total amount of mechanical energy final, right? We can break this down and make it a little more detailed, and it's already written for you there, right? Oh, 2-bar, right? We know that mechanical energy consists of 3 things, right? Kinetic, gravitational potential, elastic potential. So if we look at the amount of kinetic energy initially, plus the gravitational potential initially, plus the elastic potential initially, add the 3 of them together, we'll find that that total is the same as those 3 at the end. Now here's something we need to not get confused about. When we say conservation, we're talking about the total. If we looked at the kinetic energy initially and the kinetic energy at the end, individually there might be a change in kinetic energy. But if the kinetic energy is going to change, what else has to happen? Something else has to change as well, right? The total has to stay the same, not each individual amount of energy. Okay? Does that make sense? Okay. So let's do the classic example that you guys have at the bottom of your page, and let's talk about this lady, all right? So she's, or actually, I guess I don't know if it's a lady. It could be a man in a dress. I'm not gonna judge. Right? It works exactly the same as with a lady or a man in a dress. That's fine. Okay. So here we are. We have this person standing on the edge of a very, very tall building, or the window of a very, very tall building. Apparently, this fire has raged out of control. That her only option left is to jump. Okay. Well, no. Look at the bottom of the picture, right? I don't want to spoil it for you. Right? You guys have the whole picture. I'm just going to show you parts of it, right? So, at the moment that she steps off of the window ledge, what's her velocity? 0. Right? So what's her kinetic energy? 0. Right? At the very instant that she steps off the ledge. But she's high in the air, so she has gravitational potential energy. Immediately after she steps off the ledge, what is she going to start doing? Accelerating. That's going to cause her velocity to what? Increase. And so there is an accompanying increase in kinetic energy. But that happens as she gets lower and lower and lower. So her potential energy is decreasing. What's the total amount of mechanical energy that she started with? 10,000. Remember, mechanical energy is the sum of these, right? How much mechanical energy does she have now? 10,000. Individually, the kinetic energy has gone up and the potential energy has gone down, but the total remains exactly the same. That continues to happen, right? She's going faster and faster and faster, so her kinetic energy is increasing, increasing, increasing. Corresponding decrease in potential energy, but what's the total still? 10,000, right? And then, right before she hits the parachute down at the bottom, or the trampoline down at the bottom, right? If we call that height 0, her potential energy has gone all the way down, but the kinetic energy has made up the difference. Okay? So, yes, go ahead. Okay, so elastic potential energy is going to depend on how far something is stretched or compressed. So at this point, down here in this last picture, there would be 0 gravitational potential energy because she's at the bottom, quote unquote, and 0 elastic potential energy because the trampoline is not stretched out yet. It's all kinetic. But when she hits the trampoline, what does the trampoline start to do? Oh, we're not going to calculate it, but it goes like this. Okay? K is a description of the material, like how stretchy it is. Okay? And then X is how far we stretch it. It's something that's just like you measure it based on if I hang a weight off of it, how far does it stretch out? Like, you know,
Oh, we've done that.
this, like, yeah, like this rubber band versus this rubber band. If I hang the same weight off of each of these rubber bands, one's going to stretch out this far, the other one's only going to stretch out this far, right? So it's a measured value, basically. Like that's the only way really to determine what K is for those materials is to measure it, basically.
So there's not an exact number.
It's different for every object. So
There's still an exact number.
yes, each.
How do you calculate K?
Well, generally speaking, like I said, that's a measured value. You would be given that value, or you would determine that value experimentally, right? And then once you've determined that value experimentally, then you can use it for other applications. Okay? All materials have a value for K. Some are very high, some are very low, right? Like this rubber band has a pretty low K value. It's pretty stretchy, right? But this meter stick has kind of a high K value because it springs back pretty strongly. Does that make sense? Right? So yeah, all materials have a value for K. They're just experimentally determined. Right? So, well, I mean, you don't know how, like, it says, well, maybe, you know. I have a story about this picture though that we didn't get to today because we got to the end of class.
There's only 2 stories and they're pretty.
Yeah, maybe her mass is just really, really big, and that's why her potential energy is so high, right? Maybe she's not really that high off the air, but, you know, she has a lot of mass.